What's up, everybody? Welcome back to part 3 of the Build, Bench, and Expand series. Today we are in the expand phase. So we're going to show off some numbers that I ran to get the overall performance of this 5-node Ceph cluster today. So this is the multi-threaded, multi-client numbers, essentially pushing the cluster to its absolute peak. We're going to show off maybe one benchmark live, but I've got the list of benchmarks there. And then we're going to dive right into expanding this Ceph cluster to our full 6-node size of 6 of our F16 servers. And then in the next video, we're going to re-benchmark and see just how fast this thing can be with all tunings, with full expansion, with everything as fast as we can possibly get it. So let's dive on in and get started. All right, so we're just about ready to go, but before we dive in, what I want to do is kind of talk about what we've got. So in the first video, we built our 5-node F16 Ceph cluster. In the second video, we did a list of tunings. There were 6 really big tunings that led to massive performance improvements in our cluster. If you watch the video, you'll see that the last benchmark that we did, we actually saw reduced performance. That came from a network blip that we were seeing where we were getting a lot of slow heartbeats on the back end network, which caused some issues. So after I went in and fixed the network, reran the tests, the performance was exactly as we expected. So we did kind of improve across the board. Maybe in the description, I'll leave the full numbers afterwards so you guys can take a look if you're interested. But yeah, so after that, now we're here today, and what we're going to do is those were single client, single threaded benchmarks that we were running. We were kind of seeing how fast can we get a single thread in sequential reads, writes, as well as random reads, writes. Now this video is going to be more for how much can the Ceph cluster do IO-wise, throughput-wise, if you throw as many clients and as many threads at it as possible. You'll never be able to saturate a Ceph cluster with a single client or single thread. Ceph will just never be able to do it that way. Ceph scales incredibly well as you throw additional jobs, additional threads on it. And that's exactly what we're going to show today, that it keeps just growing in performance. It doesn't fall off until you actually saturate that Ceph cluster, whether it's the network that you saturate first or the actual disks or the CPU, wherever the bottleneck comes first. So what client environment do we have? How are we going to benchmark this? So what I have is I have 2 Proxmox servers that are loaded with 32-core AMD EPYC CPUs, 128 gigs of RAM, very performant. Each of those hosts have a 100 gig network back to the same switching as the Ceph cluster. And what we're doing is we're creating multiple client VMs on there, and we are mounting an RBD on each and every one of those clients. We're putting XFS on that RBD, we're mounting it, and then we are benchmarking through FIO all of the clients simultaneously. So we went all the way up to 30 clients, fully saturating the cluster. Some of them bare metal, and then even 20 of them were through these 2 virtual machine hosts, Proxmox 1 and Proxmox 2. So that is the stage of how we were able to saturate the Ceph cluster. What I would also say is, same way with the first benchmarks, we pre-filled that RBD up front to make sure that the performance numbers are repeatable and that we're not getting wide swings in numbers from run to run. So there's no big run variance, so we know what we're getting is true. And so I've already run a bunch of these benchmarks. Let's just dive in. I'll show you the environment that we just talked about. We'll show off one benchmark. We'll try to saturate this cluster, get as fast as we can go, and then we'll dive into the actual numbers that I've already collected before we start building our 6th node into our Ceph cluster. So let's dive on in. All right, so what I didn't mention there, I have all my clients, right? And let's just show them off here. So we take a look. We've got 2 Proxmox hosts, Gateway 01 here. We take a look at the summary. We have 48 CPU cores, so sorry, it's 24 core, 48 thread per host. These are AMD EPYC 8224P, 24 core CPUs. We have 128 gigs of RAM in each of these. We can see that here, and that's host 1. And then if we go down to host 2, we can see the same thing, same exact CPU. So we're keeping everything uniform as possible. Like I said, each of them have a 100 gigabit connection back directly to the Ceph cluster on our 100 gig network, or 100 gig switching. And we can see here a list of our VMs. These are our benchmarking VMs, so I have them spread evenly across 2 hosts. So there's 20 benchmark VMs, plus we have 6 bare metal clients as well. So we've been able to really stretch it out to have a lot of clients simultaneously hitting this cluster. So we can see these here. Each of the VMs aren't too crazy as far as specs go. We don't really need much. They've got 4 cores and 8 gigs of RAM, and they're just a Rocky Linux 9 VM. They have FIO installed on them, and they also have obviously Ceph Comet installed because we are kernel mounting these RBDs, putting the XFS file system on them. I'll show that here. If we take a look in, actually let me SSH into one of them. So let's SSH into 10.10.10.102. So this is benchmark 2, client 2. If we do a DF, we can see here we have an RBD kernel mounted to mount bench. And this is the same for every single client. Like I said, we pre-fill them to make sure that we don't get crazy run-to-run variances. So all the images are not thinly provisioned anymore. What else should we talk about here? So how are we running these benchmarks simultaneously? How are we getting FIO to run across up to 26 clients simultaneously? Glad you asked. That's where Ansible comes in. So we're using Ansible with some ad hoc Ansible commands. So if we take a look here, I'll cap the host file. These are all of the clients that are going to be running simultaneously. Now, if you want to do something like this, something you should be aware of, by default, Ansible only produces, I believe, 5 forks. So if we had, 20 some odd clients and we tried to run this with the default configuration, it's only going to benchmark the first 5 simultaneously, then it'll benchmark the next 5, etc. But we need Ansible to come in here and run this FIO command on all hosts at the exact same time. So they're all running and they're all ramping up and they're all running the tests at the exact same time. So something you should be aware of. But just to take a look, like I said, we're not using playbooks in this case. We're just using ad hoc Ansible commands. So if we take a look here, we're using ad hoc commands. And essentially what it's doing is it's taking that benchmark overhead in our host file here, and it's taking and running this FIO test on every single one of these hosts. So that is the stage set. Let's first run a little benchmark just to see how much throughput we can get out of this cluster right now. So I'm going to watch Ceph, and we can kind of see how much I/O we're pushing through the cluster at any given time. So let's take a look at the test we're running. We're using FIO. We're using a 1 meg block size. It's a 15 gig file, nothing too crazy. We're using reads. We're always going to be able to get more read performance in Ceph than writes because we can read from all OSDs, whereas Ceph, you're going to have to write to 3 OSDs for a single write. Obviously, your throughput is going to be cut by some amount. So we've got 2 jobs running. So each VM is spawning 2 threads. Each VM and each host client is running 2 threads. So we're bumping it up even further. And we're using direct I/O. Very important, use direct I/O. If we don't, we're benchmarking the RAM effectively of all of our clients. We'll get a little bit of throughput in the Ceph cluster, but it won't be true. It won't be the actual number of what the Ceph can provide. So we are doing direct I/O right through the entire thing. Time-based, and it's running for 60 seconds. So without further ado, let's kind of run this test and see what we get. Like I said, we've got all the results already done, but let's do this one for fun. Okay, so we'll get this to ramp up here. We've got our cluster here. Oh, actually, I'm going to stop this very quickly and stop scrubbing. You don't want Ceph to be scrubbing while we're doing benchmarks. So I'll wait for this test to finish, and then we'll rerun it again together. So I'll come back in 2 seconds. Here we go. So I've got the no scrub set. I let the benchmarks run through. We're going to run it here now live with no scrubbing to make sure, again, no variance. If you're scrubbing in the background, you've got I/O already in use. So we want no variance when we're running our benchmarks. In this case, it's not so important. We're not actually recording them because they're already recorded. But for my sanity, let's do that. All right, here we go. Going again, and let's watch. So again, this is a 5-node Ceph cluster, 516 drive in each node. All right, so we're ramping up, 30 gigabytes a second. It's going to go higher for sure. 46, yeah, not bad. I think we probably will max out around 50 is probably what I would guess, and we'll probably average around 35 to 40. If is in fact the same as what we were seeing yesterday. So yeah, it looks like it's pretty close. We're going between 48 gigabytes, which is like 50-ish gigabytes a second. So it's bouncing all around. We can also head over to our Grafana dashboard here, and we can go last 5 minutes. We can go every 5 seconds. And we can take a look here from the last run. We were hitting 40 gigabytes a second, and now we're running again here, so we'll let it keep updating. We'll also pull up our numbers again, so it's still running. It's probably almost done. If we take, yep, so it just finished, so that's going to ramp down now. Those numbers are going to start coming down, and then we can take a look at our graph here and see exactly what we ended up with. So there we go. We average around 37, 40 gigabytes a second, which is pretty good, really fast. Again, for 5 nodes to be pushing that many gigabytes a second. Remember, we're talking over the network here. We're not just talking locally on a machine pushing 40 gigabytes a second, which is really impressive in itself, but this is 40 gigabytes that's going all over the network, 100 gigabit network spread out across 5 nodes with LACP bonded network. So very fast, but let's take a look at the rest of our numbers. So if we pull up, we can see at the very top here, we started with sequential writes. So with sequential writes, we maxed out at about 11 gigabytes a second. But if we take a look at the actual Grafana graph and we look here, we can see it more averaged around 7.5-ish. So if we take a look at our sequential write, so 11 gigs was max, 8 gigs was average. That's what we got for our average performance. Sequential reads, so 50 gigabytes a second was our max, and 40 gigabytes a second was our average. Okay, looked pretty good. Then when we went to our random writes, this is where we don't care about throughput necessarily. We want to care about how many IOPS per second we're getting. So with our writes, our random writes, we were maxing out at about 408,000 IOPS per second, which is really crazy for a Ceph cluster. So for writes especially. And for our random reads, we actually maxed out at over 2.07 million IOPS in a 5-node Ceph cluster. And our average was about 1.5 million IOPS. So again, staggering numbers if you know Ceph. These are really fantastic performance numbers, especially because of the synchronous nature of Ceph and how all I/O has to go over the network like it does. So really great numbers, really great showing, but ideally we're going to expand this Ceph cluster and we're going to see some even bigger numbers after that. That will be in part 4 of the video, so really exciting. So without further ado, let's go ahead and hop into our Ceph cluster and let's expand it. All right, so we're ready. We've got the Ceph dashboard up here, and we're about to show off how easy it is to expand a Ceph cluster once the time comes, once you're ready. So without further ado, let's hop in and do it. So like I said, we're at the dashboard here. We can see we do have a health warning. It's just the warning because we set no scrub, so I can turn those off now. We don't need to keep them because we're not doing any more benchmarks, so let's just do it. So my sanity, again, remains intact, so I don't look at the big warning. Ceph OSD, set, no scrub, or unset, rather, and no deep scrub. Another thing you should keep in mind, right, if you're going to benchmark your cluster, you're going to want to make sure that it's not scrubbing, it's not doing other client I/O operations, so you can get the best actual realistic number. So we are ready. We've got our Ceph dashboard up and running here, and we're ready to add the host to the Ceph cluster. Before I add it though, I just want a quick little precursor that I talk about. So when we do all of our benchmarks here, I want to make sure to note that we are not doing anything that we wouldn't do in a production environment, something that we would deploy for a customer. A lot of times, if people want to get the fastest number in a Ceph cluster, they will do things in that cluster that will turn off some of the safety parameters or things that will make it a little bit less consistent, like turning off CephX will give you a little bit of performance improvement, reducing the number of log outputs that an OSD is going to maintain, things like that. There's a lot of little things that we can do that's actually going to make the cluster faster, and it's going to look great on page. We can see bigger numbers, but it's not something that you would really recommend in a production environment. So just let you know, any benchmark, any numbers that we deliver throughout this whole series would be everything that we would do in a production environment for a customer, using our best practices, using our tunings, things like that. All right, let's hop in. So we're at our dashboard. We're going to show off just how easy it is to add that extra node into your Ceph cluster once you're ready. Let's say you filled it up to 70% and it's time to add that new node. How easy is it? Well, let's just show it off. So we add a host here. We're at the host page. One thing I did previously before doing this is I just copied over the ceph.pub key. So we can see SSH copy ID, and then we are copying it to the new host. This is something I did in the very, very beginning after bootstrapping the cluster to all of the additional nodes, 2, 3, 4, and 5. So let's add a 6th host here, lab_adm6, and let's make sure that lab_adm6 is in our host file. And it is, perfect. So lab_adm6 and 10.10.10.6. Okay, and for labels, all we want this host to be is an OSD node, so that's the only label we need to add. Okay, so it's adding, and there we go. So we've now added the 6th node. We will wait and see if it added the maintenance flag or if it's going to start adding the OSDs right away. All right, so this will take not long, maybe a minute or two for it to show up here. So we'll just wait. All right, so here we go. We can see that the 6th node got added. We added the label of OSD. We can see the services that it has deployed thus far is the ones you would expect. It grabbed the Ceph exporter, crash exporter, and node exporter, so we can actually grab metrics from this host. So that's great. All right, so now let's go ahead and we can see that OSDs are already being added on their own. See, we can see 2 now, and it's just going to keep going up to 16. So we didn't have to do anything else, literally nothing. We added the host in, we added the label of OSD, and it already knows how to do the rest. It looks at those disks that are NVMe disks that match the rest of the cluster, and it sees that there's 16 and they have no file system or no logical volumes on them, and it pulls them in and starts using them right away. Now, if that's not something you want, which it was in this case, you can make sure that your cluster isn't going to automatically start adding things. But for in this case, that's exactly what we wanted, so I made sure not to remove any of the kind of safety parameters that we could have added. So we can see it's up to 8 OSDs, 9 OSDs, so it's just going to add them in. Let's pop into our command line here and let's watch Ceph. We can actually see, look, we've got a bunch of placement groups that are backfilling, right? Because now our crush map has changed. We now have many more OSDs that the crush map can look at. So now it's going to say, oh, these placement groups that used to be optimally in these locations, we now have a whole additional node with a bunch of new OSDs. Now the optimal location of these placement groups is going to be somewhere else. So now it is doing all of the algorithm calculations to say, we need to move X, Y, and Z placement groups here, here, and here. So the goal now is if we had, let's say, 8 terabytes, let's just say, or how much do we have? Let's see, used space, 2.8 terabytes of used space on this cluster, and those were across the 5 nodes. Now it's going to drain those 5 nodes to the point where all nodes in the cluster are even in how much space they have used up. Because that is the goal of Ceph, of making sure everything is extremely redundant, extremely well balanced across all nodes, across all OSDs. It gives you better performance, it gives you better redundancy and distribution of your data. So that's going to continue for the next little while. So I'll let it continue. Actually, something we can do live here to make it go even faster. So let's pop in and take a look. So if we do a ceph config dump, we can pop up and we can see there is a setting enabled for our OSD mClock profile, and it's for high client ops. So the balancer of what is more, what do we have a priority for? Recovery, rebalancing, or high client operations. In this case, we're prioritizing our client I/O. If we want our rebalancing and our recovery to go faster, we can actually change this over to say we now want to prioritize recovery. So let's go ahead and do that. So Ceph, actually let's take a look. History, grep, client. It's not there. That's okay. We can do it ourselves. So let's do this again. Grep, high client ops. So we're going to go Ceph, OSD set, OSD mClock profile, and then I can just put gobbledygook here and it'll give me the options, I think. course, I can't remember the command on the fly. So ceph config, there we go. No, it's still not right. All right, let's find it. Let's just pop it up in Google here. Ceph client ops mClock, and we will change it from mClock. Actually, it might have been this one right here. Yep. Client. You're seeing us figure this out in real time. All right, so what is the full command? There we go. Ceph config set OSD. So let's go ahead and do that. Copy, pop it over to our, and we don't want individual OSDs, we want all of the OSDs, so we're going to do that. And now if we do this, there we go. Now we can see the options. We have balance, we have high recovery ops, we have high client ops, and then we can also do custom ones. So we're just going to do high recovery for now, and we can see that our recovery will increase. And then we'll put it back to client once the recovery finishes, once the rebalance finishes. All right, so now we'll watch again. And there we go. So we're now speeding up a little faster, which is good to see. We're doing more active backfilling on PGs than we were before by quite a large number. So I'll let this finish, and then we'll come back. All right, so what we can see here is the cluster is now fully rebalanced, fully recovered. All that data has now been distributed evenly across 6 hosts. Something I did in the meantime while I was watching it go, I'll just show you. So we're using mClock on the back end, and that kind of handles the balancing of I/O versus recovery operations versus scrubbing, all this stuff that it's doing, it's handling that. What you'll see when you build a Ceph ADM cluster, if we take a look here, if you do a ceph config dump, you're going to get an IOPS capacity for every single one of your OSDs. And this is predictive that it's going to do. So you can see they're all identical for mine, and that's because I just changed them. But it was sitting between 40 to 100,000 IOPS, and it takes into that account into its algorithm that it uses when it decides how much I/O can it put towards client, how much can it put towards recovery. And the thing is 50,000 IOPS is a very, very low estimate for what it actually is capable of, what these NVMe's are capable of. So what I did was just created a quick little dirty loop to go through and set individually every one of these to 100,000. Again, probably pretty conservative, but it was just what I did to increase the recovery performance. So let's just show you kind of what I did for some fun little loop knowledge and learning. So what I did was so if we take a look at the command here, for I in, and then I have a variable. And so what I did was inside the variable is just an output of a command. So let's run that command first, because what I'm doing is I have to set a command individually for every one of these. I have to do ceph config set mClock capacity IOPS, and I have to set the number of IOPS I want for it. So if I had to do that for 96 some odd OSDs, it's really tedious and it takes a long time. So if we look at the output of that command, so if I did ceph config dump, we already know what it does. It outputs the whole output. That's not going to be very helpful for us. So if I do ceph config dump grep OSD dot, it's only going to give us the ceph config output of all of our individual OSDs. So that's nice. Gets it a little further. But if we go even a little further than that, and we ceph config grep OSD dot, and then we pipe once more, and we go awk, and we print the first column. Let's do that. Print $1. Oh. There we go. Boom, look at that. So now it gives us a list of all of our OSDs from bottom, from OSD 0 all the way to our 99 or whatever OSD. So now we have a list that we can loop through. So now if we look at our loop, we're saying for I in this big list, loop through this big list, do this. Do ceph config set, and then that's where our variable comes in, our I, of our $I, of the output of this, this little command in here. And we're saying set individually for every one of these OSDs, the OSD mClock max capacity IOPS to 100,000. So then it goes through and it loops through every single one on this list, and it sets that command for us. So that's a nice little fun way to be able to make a lot of changes very, very quickly in a single command. So I just thought I'd show that off. So what that did was that said, oh, I have way more IOPS available. I'm going to now put more IOPS towards recovering this cluster. So now we can see we have our 2.8 terabytes of storage. We have our 96 OSDs. They're all up, they're all in, and we have all of the data evenly distributed. So now if I say, for example, Ceph OSD DF, we can see, oh my goodness, sorry guys. We can see that all of our OSDs, more or less, have pretty much the same amount of data on them. So we can see raw use, 88, 94, 97, 99. So they're all very roughly close to each other. The balancer will go in the background over time and make that even closer as a much better balance between nodes, or between OSDs, but this is great for now. We have almost the same number of PGs on every single OSD as well, which is what we want to see. We can even tighten that up further and say we only want a variance of 1 PG per OSD, and the cluster will go in and do that for us, but we're happy right now. It will continue to balance in the background, but you can see the standard deviation there. But yeah, we can go further if we want to, but in this case, we don't need to. So now let's head on over to our Ceph dashboard, and we can see now we have lab ADM 2, 3, 4, 5, and 6. And if we go to our dashboard, we are in a warning state. We know the warning is just the fact that we have no deep scrub set. So we can see no scrub, no deep scrub. But we have much more space available to us because we have 16 new OSDs, and we are looking into a good state. So that's how easy it was for us to build a new Ceph cluster. If you remember, really all I did was one command. I copied over that Ceph public key, and then I went into the dashboard and I added a new host by host name and by IP address, and then selected the label of OSD, took my hands off, and Ceph did the rest. I could have just stopped right there and not done anything else, and that would have been it. The cluster would have gone completely self-balanced itself and brought itself to health okay, but I just pushed it along a little bit by increasing the number of IOPS towards the recovery to make it go a little faster. That was really all I did there. Okay, so that's it. That's how easy it is to expand a Ceph cluster in a Ceph ADM world. So what's coming up? Well, we know we've got our base numbers of what the cluster could do at 5 nodes. Now we're going to come back in next video and we're going to see exactly how much performance in throughput and in IOPS did we gain by adding an additional node and an additional 16 NVMe's, as well as an additional 200 gigabits of bandwidth to the overall cluster. So hope you join us. Hope you are enjoying this series, and I will see you on the next one very, very soon.